Log on, tune in, find out. Another good idea from Cambridge.
All right. Very quick. Let's reach the braid groups. You may notice that I'm slowing down. All right. So we have reached this point where we know the braid group called BG, which is the pi 1 of V reg mod G, which maps onto our complex reflection group, our finite reflection group. The kernel is the pure braid group. This guy is generated by the reflections, and actually the distinguished reflections, which are indexed by the hyperplanes, the reflecting hyperplanes. And this guy is generated by all the lifted braid reflections, which live above. And they are indexed this time by H and gamma being essentially a path from x naught to h. This is a quick review of what we have done. So now I would like to say a few words about, first of all, my aim is, I'm not so sure what my aim is here. It depends on the pace of these lectures. So I want to reach the Hecke algebras. I want to introduce the Hecke algebras, also with the monodromy approach. I say monodromy because I am unable to say the name which is associated to this set of equations. Zamolotchnikov. What's that? What? Is what he said? Okay, thank you. Thank you. So I want to read that point too, and of course, since it is a instructional week about Lie theory, it would be great also to reach the all the world of applications, all that things to that approach to algebraic groups, but probably I won't. So let's see. I won't have time. So let's see what comes out. First of all, I want to say a few words because it's not so well known and it's very easy about the linear characters of the reflection groups and the linear characters of the braid group. So let's pick again downstairs in the reflection group. Let's pick a reflecting hyperplane, and let me denote by JH. Why J? Why not? And also because it has something to do with Jacobian ultimately. So JH is a non-trivial element of L. Remember, L is the reflecting pair for the reflections. So L carries the non-trivial eigenvectors for the reflections with hyperplane H. So the distinguished reflection acts on JH by multiplication by e to the 2 pi I over EH. And let me denote by red, bold, whatever, JH, the product of these JH prime of all H prime in the same orbit. Then it is an easy exercise to realize that when G acts over this bold J, you get an eigenvector for this J. In other words, you get a linear character for the group G. And this character is called determinant sub H. It's kind of local version of the determinant, and its value can be computed that way. the value of the character on this vector. So once again, this is an element, this red bold JH is an element of the symmetric algebra. You see it's a homogeneous element of this is the monomial. And so the character, the linear character defined that way is computed that way. The determinant of a reflection is the determinant H of a reflection is the determinant if the reflection is in the family associated with this H. The family of reflections with reflecting hyperplane is conjugate to H, and if one is one, if not. Okay? And what is also clear, because G is generated by the reflection, the set of all linear characters is just the direct product of the linear characters of the corresponding GH. If you think of what it means in the case of the symmetric group, there is just one orbit on G on the set of hyperplanes, so this product is just one, so there is just one factor, and it tells you that the only character, linear character of the symmetric group is the signature, which is of course the determinant on the reflection representation. That's all. Okay, so this is a description of the characters of the reflection group, and now let me, according to the general philosophy, lift this up to the braid group. So linear characters of the braid groups. Well, the first thing to notice is that if you consider this element with the same notation, you consider the product of this JH to the EH. Remember, it's a bit technical this morning, but you have to remember yesterday's talk. EH is the order of GH. GH is the fixator of the hyperplane H. GH consists of all the reflections fixing with given reflecting hyperplane H. Okay. So just take this product of these non-trivial eigenvectors to this EH. Now it's not so easy. It's a tricky exercise though to prove that this delta H, called the local discriminant, the discriminant H, is fixed by G. Why discriminant? Because once again, if you think of the symmetric group, it's not written, but in the symmetric group acting with as a permutation representation, this JH is the non-trivial eigenvector. So let me call V1, V2, Vr be the basis on which is permuted by the symmetric group. So a non-trivial eigenvector for reflection is Vi minus Vj, which is transformed into minus Vi minus Vj. Okay. So this guy is the product of Vi minus Vj to the square, because in that case EH is always 2. And you recognize the discriminant of the generic polynomial. This is the discriminant. So this is the local version for any reflection group of the discriminant. All right. So since this guy is G invariant, it's dual. You see, you can dualize everything, of course. If the group acts on V, it acts by the counter-gradient representation onto V star, and you have the same notion, the symmetric algebra, S star, the set of invariant, R star, and you can transpose everything. Okay. So similarly, if I start with V star, I get the dual discriminant delta H star. All right, but an element, a polynomial, an element of the symmetric algebra of the dual, polynomial of the dual, defines a function on V. Now, a function which is G invariant defines a function on V divided by G. And since I took all these elements GH star, which are in the complement of the hyperplanes, their value on the hyperplanes, the reflecting hyperplanes, is non-zero. In other words, it sends Vreg into C star. Let me summarize. This discriminant defines a polynomial function from Vreg divided by G into C star. A polynomial function is, of course, a continuous function. So if I take the pi 1, I get a group morphism from the pi 1 of Vreg mod G into the pi 1 of C star, which is Z. In other words, I get a function which I call LH, the same function, from the braid group into Z. And I call it LH because it's the length, as you'll see in a minute. And this is, of course, a linear character of the braid group. In other words, for H in this reflecting, the set of reflecting hyperplanes, I'm working, so this is the picture, recalling what H and L are. I'm using those two notions, those two local notions, the local reflection group, GH, which is cyclic of order EH, and the local corresponding braid group, BGH, which is infinite cyclic. Okay? And this is the morphism in that case. This is the morphism which is here. And now come the lifting theorem. Let me remind you what we have already got. The set of linear characters of the reflection group is this product of, is locally determined in a sense. A linear character is just known if you know what it's doing on the minimum parabolic subgroups. Well, we have the same results for the braid group, the set, and for the same reasons, because the braid group is generated by the braid reflections. The set of linear characters, the group of linear characters of BG into Z is the product of the linear characters of these local braid groups. And let me describe, as I said, what is this function LH defined by the discriminant. It's a length because of the following property. Any element of the braid group, since it is generated by this SH gamma, is a product of SH1 gamma 1 to a certain power n1, etc. And so the length LH of such a product is the sum of the exponent ni for those i's for which hi is in the corresponding class of the indexing H. This is local. It distinguishes a class of reflecting hyperplanes. And it gives the number of times the element of the braid group turns around the hyperplane H. In other words, the hyperplane H up to G conjugation defines a unique irreducible divisor in V reg mod G, and you are counting how many times your element in the pi 1 turns around this element in V reg mod G. It's what it is. So of course, if you take the sum of the LH, you get the real length, number of times a braid reflection occurs in the decomposition. All right, and of course this is a character, and this is a character which lifts, of course, which lifts in that sense the linear characters, the local linear characters of the complex reflection group with this commutative diagram, obvious commutative diagram. All right. Now let me again in this. I just want to give you a flavor of all these nice properties of braid groups associated to finite reflection groups. The property we have just seen now, the linear characters, are very easy to prove and very general. These properties now about the centers are among these many results in this area which are known only by a case-by-case analysis, and sometimes which are not even known for all cases. Sometimes I'm going to state you almost theorem, or a theorem which is true almost everywhere, meaning that it's true for all but a finite number of. No, I shouldn't say it's true, which is proved, because it is true, but it's not proved. It's what he calls conjecture, but a conjecture that you believe really. Okay, so now from now on we assume that G is acts irreducibly on V. G is my finite reflection group. So by Schur theorem, the center is cyclic, and let me call Z the order of the center, and let me denote by zeta this corresponding root of unity. Let me now lift this up to the braid group, and let me consider this. I'm going to rewrite this short exact sequence here. So 1 goes to PG, goes to BG, goes to G goes to 1. And let me consider this element pi, which is, so you have this base point, x naught, and in a sense you turn around x naught. You make a complete turn around x naught. This is a loop in V-reg, of course, since x naught is in V-reg. So it defines an element of the pure braid group. Let me denote by pi this element. And such an element, it's clear that this element lies in the center of PG. Remember that PG is the pi 1 of V-reg. So you are in this variety, V-reg minus this number of holes of the hyperplane. So you turn around the base point. It's an easy exercise to check that it is in the center. And let me denote by bold zeta a kind of partial turn. You turn from x naught to this zeta x naught. You go from x naught to this zeta x naught by turning just around this x naught. The picture is of course totally wrong because x naught is here, but okay, you turn around x naught. You go from x naught to zeta x naught. Of course, this is a loop in V-reg mod G, since zeta is in the center, this scalar is in the center of G. So this is a loop in V-reg mod G, so this element is in the braid group in BG. Now comes the theorem. In this context, the center of the pure braid group is infinite cyclic and generated by this pi. The center of the pure braid group is infinite cyclic and generated by this element zeta bar. In other words, what you have is that this short exact sequence here gives you a short exact sequence like this, which is, of course, not true in general. It's not because you have a short exact sequence 1p bg that you have 1 zp zb zg. In general, it's not the case. Okay, what I said here, and it's quite remarkable. But let me make some comments about it. The fact that the center of the pure braid group and the braid group is cyclic was known by Garside for the case of the ordinary of the Artin braid group. It was known from Deligne and Briscorn work in case of the braid group associated to the Coxeter groups. And for all those cases, one has a kind of general proof, conceptual proof, say. In that case, it's just a case-by-case analysis. Actually, by saying you this, I'm not even sure that it is proved in very, very old cases. I'm sorry, I don't remember. You see, like physicists, I'm feeling like a physicist. Physically, it's true, it's obvious, and for some consistency reasons, it has to be true, but I'm not sure that's been checked in all cases. No one here is able to answer this question, no. Okay, but let me say a few words more about the Coxeter groups. It is known, and I'm going to come back on this question, that given a Coxeter set of generating distinguished generators for a Coxeter group, let me here take the case of BR. So you understand the meaning of the lower diagram. The group is generated by ST1, T2, TR minus 1 subject to the braid relations, and the square of the generators is 1. You just drop off the order of the generators, and you get a set of generators and relations for the braid group. It's known, and I'm going to come back on that case. But let me just quote this at the moment. So the choice of the Coxeter generating set for G defines a presentation for the corresponding braid group. And I want to interpret this element pi and this element zeta, etc. in that context. Of course, having this, one has a section, which is not a group morphism, of the surjection BG down to G using a reduced decomposition, and it goes that way. If you have this presentation for the group BG, underline S1, underline S2, etc., corresponding to this corresponding presentation for the group G, S1, S2, etc. Each time you get, you take a reduced expression, S1, SI1, SI2, and as SIL, reduced, then you can, in a sense, lift it up by considering arbitrarily this element of the braid group. And the element you get upstairs does not depend on the choice of the reduced expression, because you go from one reduced expression to another one, you only by using braid relations. I don't remember the name of this well-clear result about Coxeter groups, exchange lemma or something like this. Anyway, so you go from one reduced expression to the other one just by using braid relations. So that means that you can, once again, this element is well defined. In other words, if you take an element little g in G, this underline little g in BG is well defined using this trick. Be careful, this is not a group morphism, because the length doesn't always add up. It's not a group morphism, but it is a section. It's what I call this section. All right? Let W naught denote the longest element in this Coxeter group. Let me denote by bold G naught its lift in BG. Then the theorem is that this pi I quoted, this pi, which is the generator of the center of the pure braid group, let me remind you here, the center of the pure braid group is generated by this pi, and this pi is just the path defined as pi of t equals x naught 2 pi I t, turning around x naught. So this is the connection with the what is known in the case of the Coxeter group. This is g naught to the square. It's also known that in this context, with this notation of reduced expression, lifting reduced expression, if you get a Coxeter element and you lift it up and you raise it to the Coxeter number, you also get this g naught square, so you also get pi. So this pi is the power of some noticeable elements in the Coxeter groups. We are going to find it again when we speak about regular elements. For example, in that case, the pi is just precisely this power of the Coxeter element, S T1, T2, Tr minus 1 to a certain power. And this is the generator of the center of the pure braid group. Once again, this is a general result for which a conceptual proof is really missing. Can be checked case by case. It has done or almost done, but we are missing a conceptual proof. All right. Now, precisely, since I've introduced this set of generators and relations for the braid group, in this case of the Coxeter group, let me say a few words about what I call Artin-like presentations. Let me define what I call an Artin-like presentation. It's a presentation of, it's a set of generators, capital S, together with relations which are homogeneous, so which are written like this. I is a finite set of relations which are multi-homogeneous, that is to say, Vi and Wi are positive words with the same length in elements of S. It's well known that the Coxeter relations can be defined that way. Now comes one of the long series of theorems by David Bessis, and let me maybe state the theorem and make a few comments. Let G be a finite complex representation group, and let D1, D2, Dr be its family of invariant degrees. Remember what is this? The family of invariant degrees is that when you let the group act on the symmetric algebra, which is C of V1, Vr, then the invariant algebra is also a polynomial algebra, C of U1, U2, Ur, and the invariant degrees are D1, D2, Dr, the degrees of these algebraically independent homogeneous elements. And of course, these U1, U2, Ur are not uniquely defined, but these D1, D2, Dr are uniquely defined. And you remember that the cardinality of G is the product D1, D2, Dr. It's one of the many relations in this area. There are many more other relations. For example, the number of reflections is G, is the sum of di minus 1, etc. There are lots of relations of that kind. So let's consider this situation. Then the following integers are equal. First of all, the minimal number of reflections needed to generate G. This is the first time I state this question. It's well known that for an irreducible Coxeter group acting on a space with dimension R, the minimal number of reflections needed to generate G is R. Well, there is nothing obvious in this statement, and this is the minimal number of reflections needed to generate G. The minimal number of braid reflections needed to generate BG. Those two numbers are equal. And this number is equal to n plus nh over dr. dr is the largest degree. This strange sign here means the smallest integer, well, the first integer after this quotient. I don't know how it is called. It's not the integral part, it's the what? How is it called? 1 plus, okay, anyway, you understand. So this equal to this, where capital N is the number of reflections and capital NH is the number of hyperplanes. Here's just a remark. If you are working with groups generated by true reflections, namely reflections of order 2, then the number of hyperplanes equals the number of reflections, because for a given hyperplane, the GH is of order 2. So, but in general, it's not the case. The number of hyperplanes is smaller than the number of hyperplanes. So each time you see this number n plus nh occurring in finite reflection group, just think of the case of Coxeter groups, of groups generated by true reflection, and it becomes 2n. Each time you have a theorem, an identity anyway, for Coxeter groups involving this number 2n, just replace 2n by n plus nh, and you find the right statement for generalized statement for finite reflection group. This is true. So this is one of the examples of such a statement. You have to dualize in a sense. So once again, these three numbers are equal, and this number, this common value, is either R or R plus 1. So once again, it's always R for Coxeter groups. It's not always R for general finite reflection groups. That's what it means. And moreover, these three numbers being equal, the group BG has always an Artin-like presentation by this number of braid reflections. And by reducing modulo the order of the elements, remember that. I told you yesterday that if that the pure braid group is obtained from the braid group by just saying that by just adding the relation SH to the EH is 1. Okay, so if you start with the presentation of the braid group, you get a presentation of the finite group by just adding the requirement and the order of the reflections. That's all. All right, so now so this is a general theorem which is almost free of classification, which is something very noticeable in this area. And now let me give you some examples. Just now I'm going to give a kind of zoology. There is nothing really mathematically meaningful, but it's just a convenient notation to remember how these groups are generated. So let me, for example, define this strange diagram. What is the meaning of this diagram? We have three nodes, S, T, U. The little circles are nodes, and inside, the number inside means a relation. It means actually S to the A is 1, T to the B is 1, U to the C is 1. And now the E stands for the multiplicity of the big circle, and the big circle is a relation. Pretty much as, of course, in the case of Coxeter groups, you are quite used to consider diagrams of that type. if you put an E here, that means ST, STS, etc. equals TSTS, etc. Here you have E letters, and here you have E letters. It's the meaning of this. And sometimes you omit the E. If you omit the E, that means E is 3. If you omit the E and put 2 lines, that means E is 4. Who knows why, but it's like this. If you omit the 3 and you have 3 lines, that means that E is 6, etc. And this is exactly the same principle. So it's what I describe here, except that now you have a relation involving 3 nodes instead of 2. And so this is the meaning of this. That means STU equals, and you just cyclically turn, and on each side you have E factors. This is exactly the same thing, except that you involve 3 letters instead of involving 2. That's all. All right? Okay? And as I said, S to the A, T to the B, U to the C is 1. All right. Now, pretty much like it was in the case of the Coxeter group, let me denote by D braid, the braid diagram, the same diagram with the same braid relation. Oh, shit. And now I don't know. Help. Someone knows how to manage this damn Windows system? Hmm? What? Control L. Control L. Great, thanks. What I was saying, yes, the braid relations are written here, and the order relations are written down there. So this braid diagram means that you keep the braid relation, and of course you forget the order relations. Okay? So as I said, it represents only the braid relations. For example, the celebrated exceptional groups denoted G7, G11, and G19 by Shepard and Todd have the following presentation. So, well, I have no time to give more details about these presentations, but you can notice that they all have the same braid diagram. Okay? So that means that they have the same braid group, but not only that. They have the same set of braid relations, and now this braid group with the same braid relation, the same generators, by just giving different orders of the generators will give 3 different reflection groups. And they have lots of things in common, but I have no time to describe what they have in common. If you omit the number, that omits just 3. It's STU equal TS, TUS equals, I mean,
so
yeah.
it's 1.
Yes, it's 1. It's 3. 3. It's 3.
Okay.
Yeah, okay, the number of letters. All right. Now, for each irreducible complex reflection irreducible group, there is such a diagram D, and with the set of nodes is identified with the set of distinguished reflection. And theorem, for there is the braid reflection above, such that the set of braid reflection is and together with this braid diagram is a presentation of the braid group. So the situation is pretty much the same as it is for the Coxeter groups and the Coxeter braid groups, right? For example, the group Gn, for n being 4, etc., as the dihedral groups, they all have diagrams of type like this. Our famous group G5, for example, the group I defined the first day, G5 is like this. I omit 3. Okay? So here I describe once again this diagram, so that if you fall down on tables, you will understand the meaning of this presentation. Of course, there are some other things. The group G18, for example, are as a B2 braid group, indicated like this. But of course, it's not generated by true reflections. And finally, the most difficult group is this one. So this is a group of rank 4. This is G31. This is a very large group in the Shepparton classification, and it has this diagram, and it took many years to prove that actually it not only has this presentation, but the braid group has the corresponding braid diagram as presentation. It was done maybe 2 years ago by Bessis and Jean-Michel. Maybe I don't take time to. It will be on the web, so you can check that I didn't cheat with the and you understood exactly what are the convention for these diagrams. But you see, you have a bunch of Coxeter-like relation relay. For example, VT is here. The link between VT is here. The link between U and W diagonal is here. You have this circle, and the circle is where? Here. The circle between SU and T is here. And when they are not linked, they commute. It's exactly the same type of convention that we have for Coxeter diagrams. There is no really mathematics behind. It's just a trick, and it works. It's a fact. Okay, it's a fact that you can define this. So let me say a few more words on this recent work of Bessis, which once again is the only kind of conceptual approach on this area where lots of things have still to be done. First of all, let me treat the statement of a very old conjecture, a paper which is still an archive, and which is this general theorem, which was almost free of classification in its proof, that the space Vreg is a k-pi1 space. It was a very old conjecture. It was known for Coxeter groups by the work of Deligne. It was known for a group of rank 2 for some kind of obvious reasons, for a bunch of other groups, but the general case, including this last G31, was achieved by Bessis. And now let me turn to a few words about Springer's theory of regular elements and what Bessis did on this. It's a very old theory due to Springer in the 71, I think, in the Inventiones. And let me remind you what it is. An element here there is something coming from the past, because my group G suddenly becomes W, and little g becomes W. But you understand. So a group of a reflection group G or W. An element is called zeta regular if this element has a regular eigenvector for the eigenvalue zeta. A regular eigenvector means a vector which is in Vreg, which doesn't live on any of the hyperplane. Okay, and denote by V of W at zeta the zeta eigenspace of this element. Then this theorem of Springer, which I announced yesterday, says the following: suppose that W is, one more definition. So one says that G is zeta regular if GV is zeta V for some V in Vreg. If zeta has order D, one says that G is D regular. D regular is a zeta regular for root of unity for the D. So it's what it says. Then the centralizer of this element W is a finite reflection group, acting this time on not on the total vector space, but on the space of eigenvectors. And the set of degrees of this group, the centralizer of W, is the set of those DIs, the invariant degrees of the group, which are divisible by D. So this partially answers the question of Sasha, perhaps, or somebody yesterday, who said, what can you say about the invariance of a parabolic subgroup? And my answer was almost nothing. But in that case, yes, indeed, we can say something about the invariance of this other reflection group, the centralizer of a regular element, which is a finite reflection group, but this time on a smaller subspace. And the fact that the degrees are the degrees which are divisible by D is the shadow of a much stronger results, which says that you can, if you pick the invariance of G, if you restrict them as function on this vector space, you keep only those for which D divides their degree, then you get a set of basic invariant for the subgroups. So that is complete answer. Knowing the invariance, a set of basic invariant for the big group, you can just build up very easily a set of invariants for the smaller group. Okay? All right, so let me give you some examples of regular element. Let's start with the usual case. For W is Sn in his ordinary representation. And suppose that I pick a D which divides N. Then, if you consider the product of D cycle, as much as you can do in N, the product of disjoint D cycle, it's an element of order D. This is a regular element. It's very easy. You can compute its. You can compute that it has a regular eigenvector for the D root of unity, and its centralizer is precisely this Riesz product CD with Sn over D. And we have already seen that this group is a finite reflection group. And the set of degrees is exactly the set of degrees such that D divides Di. So this is, of course, the set of degrees. And you can check once again that the product of the degrees equals the cardinality of the group. A second example, always starting with the Weil group. Start with the Weil group of F4. Then it's a fact that there is 3 regular elements in W. The degrees of the Weil group of F4 are 2, 6, 8, and 12. So the degrees of the centralizer of a 3 regular element, which is again a finite reflection group, are those degrees which are divisible by 3, namely 6 and 12. And this is precisely our complex reflection group G5, which was the first example I started with. And that shows what? That shows that even if you start with the Weil group, this new way of constructing finite reflection group, the centralizer of a regular element, may provide what I call a truly complex reflection group. By truly complex, I mean not real. I mean at least even not Weil. And this is the right point of view, I would say, that there is no reason to think that the family of Weil groups is just closed. It's closed under taking parabolic subgroups. But if you take, for example, this new reflection group which occurs, it's not closed, and only the whole family of finite reflection groups is closed. And when you are using Weil groups in the theory of algebraic groups, I should say the way they should be used, at least for finite groups, for finite reductive groups, you'll find out that the finite reflection groups which are not real, which are not rational, occur naturally as the same way. And they play the same role, and they occur the same way. So certainly, complex reflection group in general have something to do. Now, I think you understood that our point of view is to lift up all the properties from the complex reflection group, from the finite reflection group, up to the braid group. So how to lift the theory and these results about regular elements. So as I said, Springer's theory of regular element in complex reflection groups lifts to braid group. And that also has been solved recently by Bessis, and amazingly enough, this question arose from the geometry of the linguistic varieties. It was by studying the linguistic varieties that some people became aware of the importance of these regular elements, then the importance of the action of the braid group. The braid group acts on certain sense on the linguistic variety. It has some quotients which give rise to the cyclotomic Hecke algebra, and then we have to prove theorem about them. And naturally, it turned out that there was some questions about lifting this, forgetting completely the context of the linguistic variety and this geometry. We had problems about, again, lifting properties of the finite reflection group up to the braid groups. So this has been achieved by Bessis. And let me state this theorem. Let zeta d be the distinguished D root of unity. Then the zeta d regular elements are just the images of the D root of the generator of the center. Remember that the pi this generator of the center of the braid group. Remember that this pi, such that the center of the braid group, of the pure braid group, is generated by pi. Remember this pi of t is x naught e to the 2 pi I t. It turns around x naught. By the way, it turns around x naught. So if you think a little bit, suppose that I ask you the question, what is the length of pi? Which length? Well, the length we have defined, the number of times, etc. So what is the length of pi? You have to answer the question, how many times does pi turn around every reflecting hyperplane? Right? Well, I leave you the question. No, well, I give you the answer. The length of pi is n plus nh, 2 capital N in the Coxeter groups. Of course, because in case of Coxeter groups, this pi is, say, W naught square, remember? And you all know that the length of W naught is capital N. So it's 2 capital N, but in general, in that case, it's 2 capital N. But in general, it is n plus nh. Well, remember also, so in particular, you have that pi is W naught square. I also told you that in case of Coxeter groups, if you pick a Coxeter element, C, lift the reduced decomposition of C to the braid group, raise it to the Coxeter power, and you also get pi. So here you have exactly examples of roots of pi. W naught is the square root of pi. C is an h root of pi. Now what Bessie says is that the irregular elements are just the image in G of this root of pi. So for example, the image of W naught, underline W naught in G, which is W naught, is a 2 regular element. A Coxeter element is a H regular element, etc., etc. Okay? So you can detect, yes? What? Yes, H in the I. In the Coxeter group, yes. Well, so the regular elements are just can be detected at the level of the braid group once again, and they are just the roots of pi. Now all the d roots of pi are conjugate in the, so it's a unique conjugacy class in the braid group, and which is by far the best result. If you consider so a root of pi in the braid group, so consider say underline G, which is a certain root of pi. This is in BG. So of course, G underline G goes to a little g in G, which satisfies G to the D is 1, because this guy is in the pure braid group, so D becomes 1, so it gives an element of D, right? So this is regular. Very well, and by Springer theorem, we know that the centralizer in G of little g is a finite reflection group acting on V of G zeta D. This is regular. This is Springer theorem, which I already quoted. So in the finite group, you have another a new finite reflection group. But what about above? And this is Bessie's answer. Above, of course, you can consider the centralizer in BG of this root of pi. And the theorem is that this is indeed the braid group of that small group. So the whole situation lift and everything is readable upstairs in the braid group. Okay? So this is a complete answer and a complete generalization of Springer regular element theory. And once again, this is in particular this type of this group here, which is used in and shown to act on the under the Lustig variety. And now, since I'm doing that type of things, emphasizing the braid group, let me turn very quickly to this. Can you tell me? Thank you. Scherennik, Dunkel, Obdam, etc., etc. The monodromy representation, which is behind the scene. Well, for H a reflecting hyperplane, let me denote by alpha H a linear form with kernel H. Okay, and let me consider this one form omega H, which is 1 over 2 I pi d alpha H over alpha H. And let me choose any family, any locally defined family in the group algebra. So you see, I consider this product of local group. Remember, this GH contain all the information up to a certain level. They contain all the reflections. And I take a G equivalent, a G stable family of vectors in this direct product of local reflection group. So each family defines a G invariant differential form on Vreg with values in CG, which is defined that way. Omega is the sum for H in A of ZH, where they are defined, omega H. All right? And since we have a differential form on Vreg, it defined a linear differential equation, df equals omega times f for any f going from Vreg into the arrival space CG. So since I'm sure that many of you are saying yes, 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 but they don't understand concretely what it means, let me describe you what it means concretely, what it means. It's very easy. This differential equation, abbreviated into df equals omega f, means this. df is what? df is a linear map from the tangent space of Vreg into the tangent space of CG. You agree? df of x. Okay, so the tangent space of Vreg is V. So we have a linear map from V to CG. Okay, so df of x is a linear map. So it from V to CG. So df of x for x in Vreg acts on V. So df of x. Okay. So now I have to describe the other terms. Omega f. So we multiply by f. So f of x. Of course, df f apply f of x. Now zh is given. This is the coefficient. And now we have to describe what is d alpha h over alpha h. This is exactly the same thing. The d alpha h of x is alpha h. The derivative of a linear function is this linear function. So d alpha h of x is alpha h. So it's alpha h of v, and the denominator is alpha h of x. So now it's a very concrete linear differential equation. Okay, which is once again defined by the datum of any G-stable family of elements in GH. That's it. Let me denote by GH check the group of characters of GH. And for theta a character, let me denote by EH theta the corresponding primitive idempotent. You know, it's a cyclic group. So as a basis, it has indeed the set of elements of the group, but it is also as a basis the set of primitive idempotents associated to its characters. So I'm going to use this. All right. And let me denote by QH essentially up to this coefficient, which is minus 2 pi over EH. You can forget it. QH is essentially the exponential of ZH. ZH is what? ZH is an element of the group algebra of GH. You can compute its exponential. You just apply the formula of exponential, and you find an element in the group algebra of GH. And I call QH theta the coefficient on this basis. All right? That's all. Theorem. The form omega which is just defined by this G invariant family of element local, is integrable. And so, since it is integrable, you can find some closed. So it defines a group morphism by the monodromy business. It defines a group morphism from the Broué group into the set of invertible elements of the algebra it arrives in. So a group morphism from BG into CG star. Okay? And one can be even more precise. Of course, in BG, one has these remarkable elements, the braid reflections. So one wants to know something about what is the operation of a braid reflection. So what can be said about how does the braid reflection act, or what is the image of a braid reflection? And the answer is that up to conjugation, which is here, up to conjugation by an invertible element, we are working once again in the group algebra. The image of a braid reflection is a multiple of the actual reflection in the group. A multiple by this strange exponential which is up there. So up to conjugation, we have strong control of how does this monodromy action acts on the braid reflections. And it has something to do, fortunately, with the ordinary reflection which is which is the image of the braid reflection. In other words, since we know since we know the image of the braid reflection up to conjugation, of course we know the minimal polynomial or the characteristic polynomial of the braid reflection, which is written here now. We have this formula. We have a polynomial like this, which is satisfied by rho of SH gamma. What strange formula. You will see in a minute that is not so strange. It has a lot to do with things which are well known. A lot to do. Suppose that we are working with the Coxeter group, or a group generated by reflections. Okay. Then again, the group GH has order 2. The group GH has order 2, and the group of character is also a group of order 2. And the value of the characters on the generators are plus or minus 1. That's it. So this Q is something given by an arbitrary element of the center. You take the exponential of an arbitrary element of the center, you still get an arbitrary element, right? Well, so what do you get? This row of SH gamma, let me call it TS, like this. And so it satisfies an equation with 2 factors, because this group has order 2, and 2 variables here, because there are 2 characters. And the equation is TS minus, say, Q0, TS plus Q1 equals 0. So it has to do, of course, it has something to do with Hecke algebra, and this will be the subject of next talk. Thank you.
Okay, thank you. Any questions?
Can I ask, you described centralizers of regular elements. Is it easy to describe centralizers of non-regular elements?
I don't know. I've not tried, but obviously there are lots of unknown results. Actually, the centralizer of even non-regular elements have strong connection. They are not in general reflection groups, but they are not far from being reflection group. And anyway, this description takes place in a much more general context. Actually, the case of regular element is a particular case. What is the natural setting is to consider the set of eigenspaces for element of the reflection group. To consider, first of all, maximal eigenspaces, the largest ones, and then the subgroup of the reflection group which acts really on this maximal subspace, in other words, the normalizer divided by the centralizer of the subspace, is also a finite reflection group. This is also part of Springer's theory. And it also takes place in a much more general theory involving cuspidality of, well, no, okay, it's not.
Is classification of regular elements, say, in well groups?
Yes, everything is, they have been classified totally for all finite reflection groups, yes.
And where it can be found?
It has been classified for Coxeter groups in this paper by Springer, and for maybe even for all complex reflection, I don't remember. And Jean-Michel and I did the classification at least of twisted thing, because you can do everything I've done by adding an element which acts in the complex reflection group, and you have cosets, and it has also to be studied for algebraic groups. So you can also classify. So I'm a little bit lost. I don't remember what we have done and what Springer did. But essentially, Springer did everything.
Okay. Any other questions? Okay, if no, then let's thank speaker again.